Thanks a lot, and thank you for the invitation to visit here and to give this talk also. I'd like to discuss the affine Grassmannian of a reductive group and its definition, and why its definition kind of can be made simpler than it's usually done. Namely that simply one does not need to sheafify the quotient that appears in that definition. So that will be the main result I'll talk about, and later we'll also discuss versions in analogous geometry and for a Vidal plus affine Grassmannian of Scholze. Okay, so I'll begin by describing this given result that presheaf quotient gives the same affine Grassmannian. So for this, let me fix the setting. I'll be working over base string A, where oftentimes when considering affine Grassmannian, one just is considering GLN over complex numbers, so that they would be complex numbers. That's perfectly fine. Although it's perfectly fine, that results will still be kind of interesting independently. And so I'll also fix a reductive group over this ring A. So for instance, those classically G could be just GLN over those complex numbers. And for completeness, let me just recall what I mean by this. So a reductive group is a smooth affine a group scheme whose geometric A fibers are connected to reductive groups. And well, that's a convention, but it's one used in a GP and significant one. Otherwise, theory can decompose into the theory of finite groups, used as finite group schemes, I think. Finite multiple schemes and actual and the reductivity condition is that there is no non-zero connected normal unipotent subgroup. No such subgroup as an iterate extensional chains. Okay, so yeah, so some kind of matrix group, perhaps GLN, or perhaps orthogonal group, or symplectic group, or some exceptional group like E6, 7, 8, so on, or twists thereof. Yeah, these are types of groups that we're considering here, and the affine Grassmannian is defined in terms of the loop group and the positive loop subgroup associated to such a E. Okay, so these are functors of G. This is the functor. Put right here. So the loop group is a functor LG from the category of A algebras to category groups. And L plus G, well, okay, so what's the functor? It sends an A algebra B to G evaluated on B Laurent power series coefficients in B. So that's so for two group of G, one is evaluating, for instance, if B is a field, perhaps there is. Okay, so if B is a field, then it's just K double brackets T, another field. We've got Laurent power series in K, and one is evaluating G, and then arbitrary algebra B. Okay, and the positive loop subgroup is the subfunctor in here, which sends that same E to all such points which have kind of no denominators. their value is G value of actual formal power series with no with not denominators. Okay, so then the affine Grassmannian of G is the quotient of the two. The affine Grassmannian denoted by G. It's an object that's kind of well studied in geometric representation theory, for instance. It's a kind of local version of the stack M1G that appears a lot in language program. Other subjects that are kind of concerned with all sorts of reductive groups. Representations of the vector groups. Okay, so the affine Grassmannian is a functor on that same category of A algebras, valued now in the category of pointed sets. And this is just a kind of a functor of the process LG modulo L plus G. Or since well, we want that space of process to have geometric structure to be representable in some sense, and for that at least we need to sheafify for some topology, for instance, for a topology, because the representable sheaves are definitely sheaf. I mean, schemes are sheaves even for a TQC topology, and so if your G has some reasonable geometric properties, it would need to be a sheaf for a étale and then the TQC topology. And so it's kind of by definition, it's the étale sheafification of the presheaf quotient and G modulo plus G. So this presheaf quotient is just a functor that says e to this this set of process of the loops inside loops. And yeah, it's unsorted by the class of the trivial identicals. All right, so now let me very briefly review the geometric properties that these functors enjoy. So the easiest one is just positive loops, L plus G. That's just an affine. That's just an affine A scheme. Yeah, because if you think of G as G is affine, so it's given by some generators and relations, its coordinate ring is given by some generators and relations. And so these generators need to be sent to the formal power series, B brackets T. The coefficients of these formal power series are elements of B. So that's kind of what the new generators, the generators of L plus G are going to be encoding, these coefficients of these power series that are images of generators. And then the relations of the coordinate algebra of G give some, I mean, when you multiply everything out, they give some relations between these coefficients of formal power series, and these are the relations of the L plus G scheme. So that's where this and that's how this one gets pretty simple. Now LG is it's no longer a scheme, it's an int scheme. And it's an int affine int scheme already. So what that means, means that some filter direct limit, filter direct union of affine A schemes along transition maps which are closed immersions. And in this case, in fact, it's just that filter direct system is kind of easier. It's just indexed by natural numbers, and these transition maps closed immersions. So this x0 is just nothing else but L plus G, and x1 is kind of the subspace, the closed subscheme of LG, where the generators of the coordinate algebra of G got sent to Laurent power series beta Laurent brackets T, where only T to the -1 is allowed to have non-zero coefficient, and x2 is minus 2 is now allowed to have root simplification and so on and so on. And since, okay, so that's how we get this. Okay. Now, the affine Grassmannian is also an in-scheme, but it's
just ask, so just to clarify, so if G, so G is going to embed in, oh, is it true that G will embed in GLN?
Yeah, not in this generality. Yeah, but that's kind of a common technique that in fact okay, so yeah, so okay, so let me just make a remark. There exists an embedding G into GLN of A if and only if the maximal central torus of G, so this is maximal central torus of G, if and only if this maximal central torus is isotropic, is isotrivial. Isotrivial means it splits over a finite étale cover. Okay. In statement, I may be assuming that G has constant dipole name, but it's anyway, it's not. I mean, okay, so there's a good work of Thomason, essentially, and then it's also a recent paper of Philip Shield. It's understood when a reductive group over any ring embeds into GLN, and this embedding is actually always a closed immersion. That's actually a general fact about reductive groups. Monomorphism whose source is a reductive group is a closed immersion. So there's a criterion that suggests that the maximal central torus has to split off right étale cover. For instance, if the group is semi-simple, then over any, then this is just trivial. There's no maximal central torus, and so then the group does embed into GLN, or if the group is split, it's not that.
So maybe just a follow-up question. I didn't remember some discussion against the workflow about whether this was true over the dual numbers, whether groups numbers. Oh, sorry, but this is a reductive. That's
yeah. So this is for reductive group. There's a kind of a well-known open problem. Open question is if we have any affine finite type group scheme over some ring, for instance, over an Artinian local ring, whether it admits an embedding into GLN, whether it yeah, I think that's that was open question. So that I think that's what you're alluding to, and that's kind of not known in general. Over a field, it's right. So over any. I'm not sure I'm remembering that. It's right, but there's an open question along these lines. But for reductive groups, that's a criteria. Okay, so the affine Grassmannian is also an in scheme, but it's not affine, not in affine. It's actually in projective, just like kind of the usual Grassmannian of parameterizing subspaces in a vector space is a projective scheme. So in this kind of affine setting of working over power series over a ring, the affine Grassmannian is similarly in projective in scheme. And this is at least if there exists an embedding of G into GLN, and we kind of know when it exists. And this is just because the proof of this in projectivity usually is done by embedding into GLN, first establishing it for GLN by studying vector bundles, kind of submodules of A double round brackets to the power, and sandwiching lattices between couple bonds, and then bootstrapping the result for reductive groups. And the reductivity is actually used in I mean, you may wonder, well, so I mean, there are other groups that admit embeddings into GLN. So what's so special about reductive groups that here you get in projective? The point is that if you have a reductive group embedded into another reductive group, then the quotient is always affine. It's I think called Matsushima's theorem, at least over complex numbers. And actually, that's a criterion of reductivity. If you have a closed subgroup, for instance, of GLN, smooth affine with connected fibers, and the quotient is affine, then the subgroup is reductive automatically. And so that affineness of the quotient is used to get the projectivity of these. It's used to get the interprojectivity. So affine Grassmannian is in projective and proper if and only if the group is reductive more or less. Okay, at least for constants. So from the base. So okay, so what this means is that again we have this kind of presentation of closed emergence, except that now these size are no longer affine but projective varieties. For instance, they can be chosen to be so-called Schubert varieties, and there's a rich study there about the geometry of these constituents and various kinds of sheaves on them and so on. So anyway. Okay, so that's representability properties that these objects enjoy, and so the main result that I'd like to present is that the definition is kind of can be made simpler. So the affine Grassmannian, in the generality I've set it up as actually already the Zariski sheafification of that same presheaf quotient LG mod L plus. Yeah, so that topology is simple, too strong. I mean, one can just shoot back for Zariski topology and and concretely, then that means that for local rings, one actually knows the values of the affine Grassmannian on that local ring, because then the ring is local, there are no ones with Zariski covers, and then you know that the values of the affine Grassmannian are going to be just a naive G P double round brackets T modulo GP square brackets.
Can I ask a question there? So, is it true that I guess, so the affine Grassmannian as a functor from étale to first pointed sets commutes with filtered elements?
Yes, it does, but that's not super obvious. I could explain why it does, but the thing, right? Okay, so let me make this mark. Actually, one can. Let the round brackets T be defined as the Henselization with respect to the ideal T of just a polynomial algebra Bt. And so this is a subring of the round power series of simple, in some sense, algebraic power series. Like instead of completing along the origin, you're just Henselizing along the origin. And so then you also have this Henselization with T inverted. That's then a subring of the Laurent power series. And so the affine Grassmannian is defined using this cosets like so. And it certainly is this kind of quotient. It certainly receives a map from the corresponding quotient constructed using Henselian loops. Sorry, here, and quotient to positive kind of Henselian loops. There is this map, and this map is always bijective. there's some kind of algebraic type approximation. Algebraic type approximation result, and that's done in this generality in my paper with the next equal. Yeah.
So what was that first word there? What type of approximation?
Okay. 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 Had a paper in the 70s about algebraization and approximation type results. And so, so in fact, so what this means is that kind of affine Grassmannian can be formed with Henselian loops instead. But you may, I mean, you may say like who cares? It's just some technicality, but like, but the point is that this functor that the cancellation, it does commute with filtered direct limits of rings. So if B is a filtered direct limit, say of finite type subalgebra, so where CS is often useful to express, then the power series with coefficients in B is not a filtered direct limit of power series over its finite type subalgebra side, because there are many coefficients involved. But the cancellation is a filtered direct limit. And so this result shows that a posteriori, therefore, the affine Grassmannian does actually commute with filtered direct limits of rings, because it can be formed using these Henselian loops, and then already here the this commutes with filtered direct limits. So okay, so maybe let me just say here the upshot of all of this is that the G flag commutes with filtered direct limits. Filtered direct limits of rings. And that's, I mean, that's useful. Even though from the definition of G, it's some problems.
Also, just to clarify, is this fact is also follows from the fact that G is imperfected.
Yes, I guess. Well, so yes, I mean, right. In some sense, this is more I mean, proving this is somewhat more basic than proving that it's an in-scheme, but also there's a kind of a bit of a, I could, in the defense of this result, I could also say, well, this is actually true for any G that is smooth and quasi-affine, that will need to be reductive, and I also don't need an embedding into GLN. I mean, anyway, so this is just a more general, result also.
So just to make sure, like this ink projectiveness, this is not true or not known.
So to me personally, it's not known if there's not an embedding into GLN. But it's a bit of a, I mean, for example, if I mean, I'm not. There could be people that it's known to, but this is also a bit of a question that doesn't arise so much in practice, because for most things there exists such embedding. For instance, this type of triviality, this is automatic. Automatic if A is normal. So if your base ring is normal, then I mean, then there does exist an embedding into GLN, regardless of what your reductive group is. So, I mean, the exceptional size is somehow just pretty small, so it's not like a very mainstream question. Okay, so all right, so part A of this main theorem says that the affine Grassmannian is just as risky sheafification of that presheaf quotient. And to kind of get foundation for why this could be so, I want to recall a more classical result that that says that if P inside G is a parabolic subgroup, then the quotient G mod P, the quotient, in the usual kind of sense where you sheafify even for the FQC topology, and then this quotient is a projective scheme, actually. Okay, so this quotient is just the Zariski sheafification of the functor B goes to G of B modulo P of B. And this is because parabolic subgroups right, okay. Maybe let me do an A-prime. Well, yeah, so prime is yeah. Because parabolic subgroups of the same type, and this type thing is combinatorial. I mean, just think of types of Walker. The same type are conjugate Zariski locally on the base. Zariski locally on A. So this result from the G3. And this quotient G mod P parameterizes parabolic subgroups of G of the same type as P, and any two such subgroups because of this result, they are conjugate over the Zariski locally on the base, and so this quotient can then be formed with respect to Zariski topology. And the situation here is kind of analogous morally. I mean, the group G now gets replaced by the loop group, and L plus G is some kind of parabolic subgroup or parahoric subgroup. And so G mod P kind of becomes analogous to LG mod L plus G. And so guided by this analogy, one would expect that perhaps this result is true. Kind of morally that parahoric subgroups of the same type as L plus G are conjugate statistical quantities or something like that. That's what's saying from this perspective. Okay. Okay, but there's also a part B, which is perhaps well, for which there is no analogy, which is perhaps a little bit more surprising. So the affine Grassmannian is actually just the presheaf quotient. So in fact, no sheafification is needed at all. It's a presheaf quotient LG plus G. If G is, for instance, split or more quasi-split, or more generally totally isotropic, in the sense that Zariski locally on A it has a proper parabolic subgroup. I mean, so the condition is kind of really not that complicated. It just has a proper parabolic subgroup. And proper means that the parabolic subgroup is required to meet every factor of the adjoint quotient. That's right. The adjoint group will decompose in as a direct product of according to the Dinkin diagram types, and the parabolic subgroups of G correspond to parabolic subgroups of G, which in turn correspond to collections of parabolic subgroups of each of these factors. And so then the condition is that the parabolic subgroup that one has locally is not to contain any of these factors. So somehow there's no anisotropic factors in PG. And so in particular, a split group is certainly not isotropic, and so is any quasi-split group. Because if there is a Borel subgroup, then a Borel subgroup meets this requirement. I mean, then it's really a Borel subgroup in each factor of the adjoint. Okay, so somehow for most groups that one encounters in practice, no sheafification is needed at all. So for instance, for GLN over complex numbers, the affine Grassmannian of GLN is just the presheaf quotient, LGLN modulo L plus GLN. And this has advantage of that one knows the B points. The B points are just the naive cosine set, right? Because no sheafification was needed.
To what extent do you know whether this holds for like more general affine group schemes? Like, does it hold for the affine? The additive group.
You mean where you start with a group defined over A underscore brackets T instead of A, or?
Just like the additive.
Oh, I'm sorry.
Like I just removed reductive.
Yeah, for the other, I mean, yes, for GA it will also hold. And we'll kind of, from what we'll discuss later, it will be. So these results kind of have they will soon reinterpret them in terms of torsors under G. And for additive group, there are no non-trivial torsors over any affine scheme somehow, which basically means that this also holds. But for reductive groups, yeah, there are, right, in general. There are vector bundles over affine schemes, so it's simply so anyway, so so this also holds for GA, but that's kind of not super interesting.
And like, what about like general affine group schemes?
Yeah, I don't know, I guess. Yeah. So let me perhaps mention that even without going there, so I do not know whether this part P is general reductive. Meaning without assuming the still complex isotropic. And as for part A, I'm not sure, but if you allow me to kind of use groups that are not constant, but I'll define over A square brackets T, but not over A itself, and I could make counter examples for this using some wound unipotent groups.
Thank you.
Okay, so in general, not sure what let me say, but for which part they are released.
That's a very naive question. In the case of GL3, the 2+1 parabolic and its opposite are non-conjugate. Are those of different types?
No, they are.
Oh, they are actually conjugate.
Yes, they are of the same type, right? The types in GLN are just kind of you have your M, which is 3 in your case. Now you kind of write it as a sum of either 1 + 1 + 1. That's the morale. or 2 plus 1, that's your type.
So that's just the partitions is the type here.
Right, yeah, yeah.
I see.
You have kind of partition the blocks, and I think it's long. It's long way of the conjugates. They are opposite parabolics, but they are of the same length. And in general, if you wish, a type of a parabolic subgroup is a conjugacy class of, since there's local conjugacy class or on parabolic subgroups, which also agrees with a local conjugacy class on what you see local conjugacy class. That's what the definition of a type is. Or from another point of view, is you take your Lincoln diagram and you look at parabolics correspond to subsets of vertices of the Lincoln diagram, and so that that's the type line, which vertices. Okay, so let me just give like a very naive example of this main theorem, part A. So if we have, if we give ourselves a valuation ring, if A is actually a valuation ring, fraction will A, and the reductive over H. And on the one hand, this part A tells us what the values of the affine Grassmannian on O and on K are, because no sheafification is needed because it's a local rings, right? So the sheafification will not really change anything. On the other hand, the affine Grassmannian isn't projected, right? So we have relative criterion of properness. So we know that the affine Grassmannian K points and O points are the same. So using these two facts, combining them, we can deduce something concrete, namely that if we have a K point of the affine Grassmannian, so that's represented by this kind of element, by a section of the subgroup, then that K point can be made into an O point. Okay, so that can be made into an O point. So kind of the denominators in K could be eliminated at the cost of multiplying by a positive rule. So we have this decomposition, and okay, so this is just by relative criterion of properness. And this main theorem part of A, we get this decomposition. Every K point is an O point after the ambiguity. That's and so just as an example, I mean, if H is just GM, what are we doing here? I mean, just as a sanity check. Well, here is all units in K double brackets T. Certainly, this unit is up to a power of T, a unit in the ring integers. Yeah, so this kind of decomposition is a generalization of this very basic identity. And for any age, probably if you tried hard enough, you probably could prove this, directly as one way or another. Just an illustration of what this part A kind of is saying. Okay, so let me turn to kind of moving a little bit into the direction of how this theorem is proved. And for that, first of all, I want to reformulate it in terms of G-torsors, in terms of torsors in the reductive group, because really that's what is behind here. Okay, so let me reinterpret. Yeah.
When you write
right not too close to the left side of the board on that board? Because the
Okay. Yeah. Okay, thanks. Maybe like this. Yes.
Yeah.
Okay. All right. So for this, let me recall an alternative definition and simultaneously a modular description of the affine Grassmannian. So even before talking about étale versus Zariski topology or sheafification or no sheafification at all, just that definition with respect to étale sheafification, one can reinterpret it in terms of descent for torsors and get some kind of slightly better understanding of what this affine Grassmannian is parameterizing. And this type of description is, I mean, it appears a lot in this classical thing. So, but I'll indicate how it puts it also. So, okay, so the affine Grassmannian is a functor on A algebras B that maps to the sheafification of these coset spaces. But more concretely, it maps to the set of isomorphism classes of pairs where strip D is a G-torsor over A double square brackets T, and tau is a trivialization of E when after inverting T. After inverting T, and all this up to isomorphism. Although that up to isomorphism is really not so. I mean, the functor is kind of rigid because tau kind of pins down automorphisms uniquely in the presence of this stuff. But anyway, up to isomorphism. Okay, so somehow if one thinks about this étale sheafification and remembers descent for torsors, in fact, it's slightly delicate because it's descent for the functor that sends B to torsors not over B but over B square brackets T. So one kind of also needs to use some kind of formal gaga for torsors and deformation theory. But anyway, one has this description for the affine Grassmannian. And in terms of this description, the presheaf quotient, okay, so that's just the presheaf quotient. It's a subfunctor, and namely the subfunctor of those pairs where E is trivial. Okay, so sorry. So this is a okay, so there I just made the presheaf quotient. And here, okay, so this is a subfunctor parametrizing pairs E tau with E trivial. Yeah, then if E is a trivial torsor, then its trivializations after inverting T are just sections of G over B double round brackets T. And up to isomorphism means that we can, change that trivialization up to G of B double square brackets T. That's the automorphism of trivial torsor of B double square brackets T. And so that's just kind of precisely that presheaf quotient subfunctor in here. And so in terms of this description, okay, so okay, so then by renaming this kind of D to A, the main theorem reduces to the following. Well, one can reinterpret what the main theorem is saying in terms of this modular description. And perhaps let me just take a new board so that. So the main theorem reduces what I will call main theorem prime. So here I have G is a reductive group over an arbitrary A. And I assume that either case A is what A is semi-local, setting that has only finite many maximal ideals, so A has finite many points, or I don't make any assumption on A, but I assume that G is totally isotropic. So these two cases kind of correspond to the cases A and B in the main theorem. Case where no series specification is needed, so kind of allows you to take A local, but then local here. And B is when the group is totally isotropic. Okay. So if I then use assumptions hold, then no non-trivial G-torsor over A that was for brackets B trivializes over A temporal ground brackets. Yeah, in terms of this modular description, that's just saying that this torsor E that appears there is trivial, right? Because it must be trivial because it is trivial after inverting T. So this main theorem prime is just saying that if the torsor becomes trivial after inverting T, then it is trivial to begin with. So then that corresponding point would have to land in this subfunctor. That's so that like, and this part of the theorem like really implies that the main theorem. But there's so then we get that the affine Grassmannian its A points are just the naive coset. Okay. And in fact, there's a little bit more. In this case, B, when G is totally isotropic, we also have that the loops of G kind of decompose into loops that are algebraic and loops that are positive. So one has this decomposition like so. And what this means that the affine Grassmannian of A is then can be formed using even algebraic loops. So when the value is G on Gm, modulo G on G1. Yeah, this decomposition that I'm creating here says that kind of every element in the quotient loops modulo positive loops. It's actually represented by an algebraic loop, by a loop which has only 5 to many coefficients. Yeah, it's just and so then one also gets this kind of. I mean, previously I told you that this is generality that affine Grassmannian can perform with respect to Henselian loops. That was this L-kick approximation itself. And here, if the group G is totally isotropic, then actually it can be formed using algebraic loops. For instance, what you learned. This is so. And this decomposition is quite concrete, right? But the point is, it's not so clear how to prove this decomposition directly, even in the case say when A is just Z, G is say K1. Yeah, so you have some n by n matrix, which is with coefficients in Laurent power series, and it's invertible. Then you need to make it, you need to make its entries algebraic at the cost of it multiplying by a matrix which has no denominators in T. And this is the way that's the kind of statement that this is saying. And perhaps to give a bit more context, let me again compare this with the following result, which is so-called Birkhoff decomposition. So if for a reductive group, for a reductive group H over a field K, you also have a similar decomposition, in fact, an even finer decomposition. You have this is a union, even a disjoint union over dominant co-characters. So here S and H is maximal case split maximal case split chorus.
The first G is 11H. Just the last G.
Oh yeah, I'm sorry. Yeah, I just don't want to. I just want to stress that it's an arbitrary reductive group, not necessarily a. So this kind of Birkhoff decomposition is as follows. Again, any loop can be made algebraic. I mean, not only algebraic, but like with values in the opposite A1, then multiplied by t to the lambda. So what is this? This so first of all, what is this lambda? So lambda completely is a map from it's a co-character. It's a map from GM to S. This is this is all defined over K. And now over this is lambda, and this is just kind of the image of T under lambda. I mean, T is a unit in GM, right? Over K double round brackets T or over K T plus or minus 1. And so then it makes sense to kind of look at the corresponding section of S, and that's what that is. So that then is, this section of H. And so one has this decomposition called the Birkhoff decomposition, and these terms, these are all in here, right? Because yeah, like this part is even better. I don't need kind of any denominators in T inverse, it's just polynomials in T inverse. And here I do have the denominator, but that's yeah. Okay, and so this is kind of a similar decomposition over arbitrary A. And they cannot be such a binary I mean, here I have an even disjoint union, but like this is specific to fields, and it's also kind of, I mean, it's not holds for arbitrary A because basically there's the specialization between different strata and Grassmannian or in what G. Anyway, this is just
So sorry, what makes it difficult, what makes this Birkhoff decomposition not work is when A is Z. It's the fact that it's not a field.
right. Yes.
Okay.
Yeah. So even this, I mean, even this thing is not so easy to process. So I mean, okay, it's a classical result, but it's not. But yes, right. So like the main difference between here and here is that here A is not a field, and then in fact A is basically arbitrary ring. So it's this even when they see it's pretty delicate to understand the values of G and
Is it
Well, yes, it is. So if G is G1 or Gm in other words, and you say A is reduced, then any unit in here is sub to the power of T, a unit in A double square brackets T. So then the kind of it's just all about unreduced structures and yeah, so yeah, like it's okay, so this main theorem prime is kind of really what we want to prove. It kind of includes the main theorem and also even finer statements like about this kind of decomposition, which actually does not follow from there. So let me then before making a great break, let me reformulate this main theorem prime once more. And kind of globalize the problem. In some sense, instead of studying the affine Grassmannian, I will now implicitly start studying 1G global version. And then by using the geometry of 1G, is how this main theorem prime is proved. Okay, so I'll pass the torsors over these formal power series to actually torsors over projective line. So let me call this G-torsor E, this torsor E over A double square brackets T, and this E becomes trivial after inverting T. So I can patch this E, I can use the last law patching to patch it with the trivial torsor. Well, in fact, let me call it curly E in just because we use application. Okay, but by patching this curly E with a trivial G-torsor over P1 minus the origin, we reduce this main theorem prime to the following. Okay, so then we have two parts. The first one is if the ring is single local, but the group is arbitrary. So for an arbitrary reductive group G over a semi-local ring A, every G-torsor E over E1 of A is such that it's section-wise constant. In other words, more concretely, the restriction of E to T equals 0 is isomorphic as a G-torsor over A to its restriction over at infinity. So in other words, equivalently, after isomorphism, the G-torsor has to come back of E that doesn't depend on the A point S. That doesn't depend on this. If we enter to section 2, you choose restriction of the torsor as long as the ring is semi-local, the restriction of that torsor is still the same. Okay, and the part B is when the group is totally isotropic. So we're totally isotropic. Effective group G, and now over any ring A, and the G-torsor again, G-torsor E over P1. If this torsor restricted to infinity, or torsor restricted to infinity is trivial, then the torsor restricted to A1, it's also trivial. That's right. If the torsor is trivial to infinity, then it's also trivial not only at the zero section, as part A would imply, but actually on all of A1. And this implies this main theorem prime, because part A is kind of when the ring is semi-local, so we had our torsor that's kind of at the origin, that's trivial on the puncture common neighborhood of the origin, and we patch it to get a torsor over P1. That patched torsor is certainly trivial at infinity, right? Because we're patching with a trivial torsor. So now the ring is semi-local. It says that the restriction to t equals 0 and the restriction to t equals infinity are isomorphic torsors. And so restriction to t equals 0 is then again a trivial torsor. And then you just kind of use the smoothness of the torsor to lift the trivialization of the t to the trivialization of brackets t. And for part B, G is totally isotropic as is there. So again, by the patching, we obtain the torsor over P1. We know that the torsor is trivial at infinity, kind of by construction. So then it says that the conclusion says that it's even trivial over all of A1, particularly trivial at 0, which is what we're claiming here. And this kind of finite decomposition is, I mean, it also follows in this part B, because like to get the triviality over A double square brackets T, we only use triviality of this at T equals 0. But if we use that the patch torsor is really trivial, like already over A1, then we also get that decomposition, because if the double coset class had some non-trivial, right? If the corresponding double coset was not just double coset space was not trivial, we would be able to glue up a torsor which would like contradict this stronger this expanding. That's kind of how that final decomposition is put. Okay, so maybe let's take like a 5-minute break, and after that I'll discuss how this theorem is proved, like what goes into its argument, and then later also discuss the Biedermann plus affine Grassmannian and the analog of these results for in that setting. So let's assume that, and so let's turn to discussing how this theorem is proved. And so let me mention right away like what the sort of end goal is. So so this theorem is proved by like the whole strategy. All can be reduced to the case when A is a field. And in the case when A is a field, there is this kind of, let me call it, classical theorem. So somehow I'm claiming that the case when A is a field is classical, this theorem. And more generally, so let me say that if we have so for a reductive group H over field A, H-torsors the single point are the same as inflations of S dot so they all come from the line bundle of one via some co-character. So let me say from one that's triviality infinity reduces the G-torsor. Yeah. Yes, from GM to H. And G-torsors are just line bundles. These are powers of one, right? It's just all events. And for an arbitrary reductive group H, it's torsors over P1. So first of all, if it comes from a line bundle along some co-character, then certainly that torsor needs to be trivial at every point, right? Because the line bundles are, trivial away. Yeah, the line bundles over field are trivial. So that's kind of a necessary condition. Like the triviality at infinity at the single k point is necessary for a torsor to reduce to a line bundle. And what this is saying is that it's actually sufficient. So just as an example, imagine that H is GLN. When Grothendieck's theorem says that any vector bundle on P1 is a direct sum of all events, right? And more concretely, or in other words, what that means is that there's a map from GM to the diagonal torus. Kind of weights there are given by the ends that appear in the decomposition of your vector bundle, and the vector bundle decomposing, coming from some line bundle over like GM. It says precisely that, right? Like in the case when H is GLN, which just covers the classification of vector bundles on P1. So anyway, I'm not sure I explained this super clearly, but this is not really. The statement is not super difficult. So, like, if the torsor is trivial at the point, then it comes from some torsor under GM via some co-character. And then then you can, then you know whatever you want to know about the torsor, because certainly a line bundle is trivial on A1, so torsor is trivial complementary A1, and like on this theorem becomes kind of trivial at A is at the end. So now the whole kind of goal is to reduce eventually, to reduce this theorem to the case of a field, from an arbitrary A to the case of a field. And so again, so this involves kind of a couple of quite pleasant techniques that I would like to.
So can I just about this factor of the argument? So the main theorem, it's not immediate over a field. You're deducing it from this sort of classical results in the case of a field.
Yes. So
up here you can have like some sort of P1 family of G-torsors over K.
Yes. So the main theorem was that kind of Zariski sheafification suffices for the affine Grassmannian. So what that statement says is that not only that the k-valued points of the affine Grassmannian are as you expect, but actually for any local algebra over a field, the a-valued points are as you would expect. So even if you're kind of starting from a group that's over a field, the conclusion of the main theorem would still involve some rings A which are not a field, and you would still kind of need to know something. Yeah, so somehow these non-field A appear even if you're studying or complex numbers. Okay, so let's review these reductions. So first of all, in part B of the theorem, the ring is arbitrary. So one first kind of fixes that. To reduce theorem B to local rings A, one uses the following lemma, which actually is really pleasant. It's well in patching, but generalized by Gaber. Gaber fluid patching. So fluid patching was for vector bundles for G1 torsors. and it was used. It was one of the main ingredients of this resolution of Serre's problem about vector bundles on affine spaces. If you have affine space over a field A to the n, then every vector bundle over A to the n is trivial. That was Serre's kind of problem, sometimes called conjecture. Within Suslin solved that and couldn't introduce a patching technique. That's what this lemma is about. And Gaber generalized it beyond vector bundles. Also building on other conversations. So, if we have a locally finely presented group scheme or even group algebraic space H, over ring A, so the point of average generalization is that the group is really very general, just locally present. Locally finely presented doesn't even need a scheme, right? Okay. So certainly a reductive group is more than satisfies these assumptions. So the G-torsor, over the affine line over A descends to A if and only if it does so Zariski locally on A. Okay, so we have some group script G, which is very general, and we have a script G torsor over the relative affine line over A. We're wondering when is that torsor constant? When does it descend actually to a torsor defined over the base ring A? And there's a criterion, namely, if you want to know that it descends to the base, it suffices to check after base change to the local rings of A. If the torsor after base change to each localization at maximal ideal descends to the corresponding local ring, then it does so globally. So this is some kind of local to global sort of patching that Quillen first introduced in the case when G is GLN by clever argument, and then later Gaber generalized magnitude local presented with those bright space. The argument is beautiful, but I will not go into it because it's not kind of really the main point of this stuff. So anyway, so somehow for this theorem B, one applies this lemma sort of twice, first to the complement of infinity and complement of zero, to kind of reduce this whole problem in part B to the case of a local ring. And here, note actually that this kind of conclusion that the torsor is trivial not only at zero, but actually on all of A1 is what is important for that lemma to kind of apply. Because the lemma is about torsors over A1, not torsors over simple. So this, like, the conclusion is kind of rigged also in a way that the lemma will be applied. Somehow we're proving here more than we really need, but that's also because we, if we were proving less, it would be more difficult to do that somehow. Not fun. Okay. Okay, so that's so kind of after this, then we can assume that A is local, and then somehow this part B reduces to part A. I mean, there's this finer thing about E over A1, but yeah, it more or less reduces to part A. Okay, so somehow we'll focus on part A, more or less. So the proof of this theorem, part A, uses somehow it's built on the geometry of 1G. This is the algebraic stack. Algebraic stack over A, parametrizing parameterizes G-torsors over E1 of it. Or if you wish, by definition, it's just a restriction of scalars along the map E1 goes to A, also the classifying stack D, B, B, G. G over. Yeah, so the points of a variable A algebra A prime is just G-torsor for one of A. Okay, so this is a very well studied. There's a lot of there's context. Just an example, how will we use this kind of geometry? So let me describe the stack in a very simple case. So if we're considering, instead of a reductive group, slightly simpler situation, if we have an A group M of multiplicative type, and we want to understand torsors over M torsors over E1, so we kind of want to study points of one M. In fact, we can understand this one M itself. It's just the constant torsors times the co-characters of M. So these are kind of constant torsors. The torsors that descend to the base, and torsors that are already coming from the base. And these are the co-characters. So these are maps from GM over A to M. So how does such a co-character give rise to a torsor? Well, you can kind of push. You can inflate along alpha. Or the GM torsor over O of 1. Now, when you have this assignment of O of 1, view it as a GM torsor, then you have this alpha, you can upgrade it to an M torsor. So that's when an alpha gives rise to an M torsor over P1. And then this formula is just saying that over any ring, or any scheme, even kind of, so an M torsor over P1 will be kind of a direct sum of the constant torsor which descends to the base, and this kind of torsor comes from a line bundle. So this, so for example, if you just take M to be GM, you get that the current group of P1, well, no matter what the ring is, it's just the current group of A times Z. Well, like if A is not collected times 4. It's just kind of a geometric reformulation of geometric generalization of this kind of well-known. Okay, and so for if G is just M, then both part A and B of the theorem follow from this. Yeah, you understand that the torsors is like constant times spine bundle, and then yeah. Okay, and so to proceed in general, for a general reductive G, we'll use the following proposition.
What is the? You mentioned it.
It's locally on A. The Cartier dual is just a constant. For instance, M could be a torus. Yeah. Okay. So in general, we use the following proposition. Yeah. Okay. So for general reductive G, we use the following proposition, which says that the map from constant torsors over P1 to all torsors over P1, this is actually an open immersion. Yeah, so this proposition is specific to P1. I mean, this bond G is studied for any smooth curve, but the fact that the map from constant torsors is that this is really kind of an open stratum, these constant torsors, that's specific to P1, and this is proved using deformation theory. I mean, the argument's kind of geometric, right? I mean, first, it's not so difficult to show that it's fully faithful, and then you need to show that perhaps it's formally smooth. That would be nice, and kind of that would imply flatness, for instance, and so to get formal smoothness, it's a deformation theoretic question. So for that, you use these volumes from LNM and do some computation with cotangent complex or with some differentials. Yeah, and that's in that computation, that's where P1 is important somehow, because H1 of P1 with trivial coefficients is zero. That's kind of what's specific. Okay, so that's a nice geometric fact, and that's actually kind of really useful if we think about what we want to prove, because we want to study torsor over P1. And it says that if we know that at the closed point the torsor is constant, then it's constant over all of A, if A is local, right? Because an open immersion, if it captures a closed point, it already captures all of the spec of a local ring. So kind of that's how this proposition is used. And then there is okay, so this will kind of allow us to reduce to the residue field, except we need to make sure that on the residue field our torsor is actually constant, which need not be the case. So now we modify the torsor to make it trivial over the residue field. So let me tell you what the main ingredient in that is. So for this, so this is based on the following theorem of Borel and Ditz, which is actually a really useful theorem and kind of should be known kind of more broadly than this. And so what is okay, so what's the slogan of this theorem? It's that the Whitehead group is unramified. So unramified nature of the Whitehead group. A plus sine JK. That's kind of a subgroup generated by elementary matrices. Anyways, let me give you a precise statement. So if we have a simply connected simple group, and we also assume that simply connected group is totally isotropic, so it has parabolic subgroups. Simply connected totally isotropic group H over a Henselian valuation ring, Henselian, let me just say DVR, Henselian DVR, DVR D. Will denote its fraction field by K. So the claim is that this quotient of GK modulo GB is, yeah, so every element, every coset here is represented by a product of elementary matrices. Let me be a bit more precise. What do you mean by that? So fixed opposite parabolics, like really proper parabolics in a limit factor. Parabolics P plus minus of G, these have unipotent radicals. Let me just call this group plus minus here. Okay, unipotent radicals. And then what this is saying is that every element in this coset is represented by a product of elements, each one of which is either a k point of u plus or a k point of u minus. So yeah, so every element is represented by one m, where each ui is either in u plus or u minus, and it's a k point. Yes. So in GLN, you think about the kind of upper triangular Borel and lower triangular Borel, and the unipotents are where you have ones on the diagonal, and so the elementary matrices are like you have one non-zero off diagonal entry, right? And so so you're just considering all these elementary matrices, one non-zero off diagonal entry, and you multiply them in the right way, and you'll be able to obtain any class in this coset. So this what kind of this Borel-Titz theorem, and in general the kind of the subgroup generated by all these elementary matrices is Whitehead group GK plus, and it's related to Knizet this problem, so on. It's kind of open questions about it, but I mean, it's a pretty interesting group theoretic kind of direction. But what this gives in the setting of kind of affine Grassmannian, or what's relevant for the affine Grassmannian, is this kind of thing that points of the affine Grassmannian can be represented by these products of elementary matrices. And it's actually, this is really useful because it sort of tells us that you have the affine Grassmannian, like this is often just like K double row brackets T, and this is K double square brackets T. That's kind of an example of the situation. And then you have the affine Grassmannian with K points. And what this is saying is that if you take a kind of product of these loops of unipotent groups, then you will get a surjection. So every kind of element here is a product of these loops on with values either u plus or u minus. And for instance, this also works in the context of the Biedermann plus affine Grassmannian. One can use this theorem also to simplify, like slightly simplify some proof in for Scholze, where it's kind of anyway, it's a useful thing. It's not so well known, but
so this is true for any choice of these problems.
Right. Yes. Right, for any choice of these opposite parabolics, and it doesn't matter which ones. So somehow, when you start taking all these products like so, one thing that gets proved is that the set of all such products, it does not depend on the choice of these opposite parabolics. You can choose any two or all of them, or So, and then that's this kind of GK plus Whitehead group is just it's just a subgroup which consists of all these products like that. Okay, so somehow, so what's the point of this theorem for our purposes? Well, we need to modify, we have our torsor E over P1 of a local ring, or semi-local ring, but after thing we can assume it's local. We have a torsor of P1 over local ring. We want to modify it at infinity, kind of do it differently a little bit, so that the torsor over the residue field, over P1 over residue field, became constant. Then we could apply our BG into Bungie open immersion lemma and kind of conclude everything with one. So we need to change the gluing at infinity. The torsor is glued from some torsor over A1 and a trivial torsor at infinity. We need to change that gluing. Now, over the rest of the field, we know that we can have a gluing which gives us a constant torsor. That's basically because of this classical theorem. And that gluing is precisely kind of the element of this quotient, G of K double round bracket T modulo G of K double square brackets T. That's just this kind of quotient parameterizes these gluings sort of at infinity. I mean, if T is the inverse of it. Yeah. And so what this is saying is that kind of any gluing, whatever gluing you have on the residue field, it's actually represented by product of these elementary matrices. And now the point is that elementary matrices live along arbitrary surjections of rings. You have a local ring and it surjects onto its residue field. And you have all these elementary matrices over the residue field round brackets T. All these elementary matrices will lift, right? Because it's just, you need to specify some of the diagonal entry. That's kind of A double round brackets T surjects onto K double round brackets T. And so these elementary matrices then all kind of lift to corresponding matrices over A double round brackets T. And that tells you that the gluing that you need to realize over the residue field can be made already over A. So you can really change your torsor over A already in such a way that over the residue field, the right thing happened. And then you conclude kind of. So this is like the real key point. Okay, and simple connectedness is important here, but then there's like, for what we want to prove, there's an additional step to reduce to simply connected, and it kind of involves studying gerbs over P1, gerbs over multiple type groups. Is okay. Maybe I'll just not really discuss that, but instead turn to the B-drum plus affine Grassmannian situation. So this is kind of the main sort of input. Yeah, and you also see why local isotropicity assumption was kind of important, because this theorem of Borel and this is actually for groups that have parabolic subgroups. That was important. So that like that's where that assumption kind of percolates throughout all of the results. Okay, so let me then discuss the case of the B-drum plus affine, which actually, surprisingly, is actually kind of simpler. So the results are. Yeah. So sorry.
I thought we were proving case A when we have this.
Yes, right. So there's like an additional step that goes into this part A, where we kind of secretly find some closed subscheme of some finite étale closed subscheme of P1, along which the group is totally isotropic. And then we do our Borel-Titz theorem with respect to that finite étale closed subscheme. Anyway, there's an additional trick to reduce part A to totally isotropic case in some sense. Part A is but if you want to get the triviality over all of A1, then you don't have the flexibility of finding that extra finite étale closed subscheme, and then you really need to try simplicity to be able to adjust that into the Okay, so let me describe analogous results in the case of in Scholze setting of B-drum plus Grassmannian perfected. So here the setting is a little bit different. So let me just review the definitions. So I'll fix a non-Archimedean multiple field A. A zero of integers. Yeah, so K is probably something like UP and OK is ZP. Be more general. Okay, and so now the test category for kind of forming these loop groups and so on will be perfectoid rings. More precisely, perfectoid OK algebra pairs A plus. So it's either perfectoid algebra over K or perfectoid algebra over the rest field of OK, in which case it's impossible to test. It's kind of encapsulates both cases in the same time. Okay, so any such has its fields, right? We can build together a perfectoid pair and equivalent characteristic. Yeah, and we fix for that field, we fix it to the uniformizer. Flat. Okay, and so we have the ring A_nth, which is just the bit vectors. And since we're doing it relative with respect to this kind of not necessarily ZP, not necessarily QP, not necessarily ZP, so we do like OK typical vectors. A plus it's the analog of A, and we have a map theta. This is from here. The original A plus characterized by sending 5 Miller elements to the compatible p-power system of compatible p-power rules. Field is now an element of the operation. Okay, so that's just sort of notation that we're using. Now, one has that the kernel of this map theta is a principal idea. Set in more fancy terms, perfectoid ring is the same thing as a perfect prism, even an oriented perfect prism. So this kernel is the ideal I that appears in the prismatic theory, and the principality of it is what gives the prism an orientation. So it's generated by a non-zero divisor. Thanks. It's assigned. Okay. Yeah. So double zero divisor psi. Like so, and the same psi is kind of a general part of the general theory that the same psi works for any kind of pair that's an algebra or an initial pair. So you don't need to change the sign.
So here K is discrete, right?
Right. So sorry, this may be a little bit confusing. So K is like coefficients in some sense. It's yeah, right. It's a non-Archimedean local field. So either K is a finite extension of QP, or K is isomorphic to FQ brackets. So just concretely just these kind of cases. There's no K does not play the role of a perfected field, but it plays a role of coefficients. And the case when OK is just ZP is the most common one. It's just the usual typical factors. Okay, so now the mixed characteristic analog of loop groups and so on. Well, so first we need to discuss what we evaluate. So the mixed characteristic analog of this formal power series ring with coefficients in A is the ring B_RAM plus of A, which is the completion of the with our contain curve at the point corresponding to the given kind of until A plus, or more concretely, it's we have these slip vectors. This A and 3, we invert the Teichmüller of the pseudo uniformizer, and then we cyclically complete this thing. And then if you the analog of the power series, let's say the ground, and this is just the ground plus with the sign. So that element psi, which was a non-zero divisor, it stayed a non-zero divisor after localization. After completion with respect to it, it's still a non-zero divisor. And after, well, and then you invert it, you get this bidram of A. So if A plus is a perfectoid field, then bidram plus of A is a stipulation ring. Bidram of A is a structure. Just like K doubles for brackets D is a stipulation ring, and K double for brackets D is a structure. Okay, so let me just quickly run over some examples. So first of all, if K is a affine extension of QP, so characteristic 0, and A is a K algebra, then these rings be down plus and beta I. Okay. These are also K algebras. And if you choose A to be CP, the completion, the completion of QP bar, then these really the bidram, then this bidram A, then really is contains period bidram. Okay. Second case, the case over QP finite, again, but A now is an algebra over the density field. So okay, uniformizer algebra. Then the bidram plus of A is just the bit factors. So then A is a perfect algebra. Bidram plus is just its bit factors, and bidram is the bit factor with invert. Then in this case, you can choose psi and B, and that's kind of what you get. So, okay. And finally, the final case is one K is isomorphic to Q double from brackets set that. So then A is also an P algebra, and so in this case, you kind of recover the usual affine Grassmannian, more or less, namely that bidram plus is just a power series link. So this is power series from the variable kind of P minus delta, or that is by K minus zeta, or by K is a uniformizer and K, and then the math theta just kind of kills this ideal. The math theta is the math which associates the constant term. And bidram of A is a monopod. It's a bar power series. Okay. So now we have the analogs of these rings on which using which we build our loop group and constant loop subgroup. but we also need the group, so we fix a reductive group. Reductive group scheme G over OK, or respectively it could be just over K. If we restrict our test algebras to be K algebras. Okay, so then we have the group G, which is functoid is perfectoid OK algebra pairs A plus, and sends such a pair simply to the value of G on B derm of A. And by the way, I didn't mention, but like this B derm of A does not depend on A plus, so that as notation suggests. That maybe this is possible. Okay, so and we have the positive group subgroup and plus G subcontract here, which is since A plus the G of beta plus. Yeah, this is so this is if G is only defined over K, then we restrict to A plus also, which are K algebras. So that this makes sense by example one. And so then the definition of Scholze of the Grassmannian is that okay, so the literal plus affine Grassmannian based on the geometrization of the line ones correspondence as indicated by Scholze, and this was introduced by Scholze in the lectures 14. Okay, so we multiply this. Is again, we want to get a reasonable geometric object, so we sheafify for the étale, or maybe even for a topology. It's the étale sheafification of for the étale topology on these perfectoid algebra pairs of the presheaf quotient. Oops, modulo positive. So same definition, just the factors are different than the classical case. Again, you take oops modulo positive, oops, you sheafify for the topology, so that you have hope of getting geometric objects. Then you prove some representability here by actually for diamonds or something. But I mean, it doesn't really matter by what is representable for what we're going to be discussed, but what we'll be discussing, but there is also a representability result in this setting. And so the main, so then the result that I'd like to mention in this setting. So okay, so then kind of that implies is that you get even a V topology for the topology, but even for the V topology. Just like if you sheafify for the topology in a classical case, you've already got an FPQC sheaf. In fact, you've already got something representable by an in scheme. So okay, so the analog of the results that I've been talking about for the classical affine Grassmannian is this the plus affine Grassmannian of Scholze is actually the sheafification of the presheaf quotient G modulo n plus G for the analytical mode. The analog of statistical topology in the second half of the geometry is the analytic topology is of for the analytic topology on the factor of the pairs. Okay, so that in fact, the étale sheafification was really kind of not necessary. One can really get the same result by just doing the analytic topology of just open something. For the corresponding small A plus and then I mean, I don't have time to go into but this is actually simpler than the classical case. It just kind of uses the main input privilege. Abelian invariance and optimization. But for G-torsors, kind of in the style of it. But this time, not with respect to the Abelian pairs. So this would be like when so somehow if we fix a point of star A plus and we look at the kind of the system of all analytic neighborhoods of this point, we take the limit of these neighborhoods and then complete in the end, we just get the complete residue field. And the torsors, so kind of G-torsors are residue field. Okay, and the other ingredient is gotten the Z conjecture for this calculation. So it says that if you have a reductive group scheme over a DVR, then any torsor which is trivial over a fraction field is trivial. And the way it's relevant is that this completed residue field is the ram of it is a discrete relation here because it's a perfected field. And you have a torsor which is trivial over a fraction field over the ram, it must be trivial by drawing subconjecture for DVRs, which is a result of this image. Anyway, let me just stop this. I don't know. So yeah, one can ask, could it be that actually no sheafification is needed, just like it was in the classical case if you assume that she is split, for instance, so totally isotropic. But I don't know. But, I mean, that whole improvement sort of came from this Gabor-Klugen presentation, Gabor-Klugen patching, where it had a torsor over A1 and you wanted to send it to A. And here it's just, you know, it's just kind of different here. There's no A1 floating around in the argument. Like the argument is different, and I don't know what I don't have counterexamples, but I also don't know. Yeah.
Is there an analog about this result in if you were working with addict spaces, not necessarily perpetually? And it's sort of the Peter plus corresponding. Like the R series?
I'm not sure, but I would. So you want to consider kind of adding spaces and analytic topology on them, but form the affine Grassmannian with respect to usual kind of loops, not to be grand plus, but just a double round brackets T and double brackets T. I don't know. I mean, I don't have anything. I haven't thought about this variant, but I like whatever the classical result specializes to in this case. I mean, it says the classical result would say that sheafification. Sorry, I mean the result in the classical case would say that sheafification for the Zariski topology, which is kind of even better than sheafification with respect to analytic topology, I think, because Zariski topology on that space is, you know, closer to no topology at all. Rather, analytic topology has all these opens which are not Zariski open. Yeah.
Main question, what applications do you have?
I mean, I don't have an application in mind that it was more that the way I came to all these results is by studying Godin-Serre conjecture, which is not something that we talked about in this talk, but it's about torsors and the reductive groups of irregular rings, and by studying stuff that goes into proofs of cases of that conjecture, and then it just, I mean, it just came out by accident that these types of results must be true, because like the arguments that go in there are give these conclusions. So, I mean, in short, I don't have like a grand application of this kind of result. It's just a cute fact if you want that the definitions can be made simpler. But it's also that, you know, it probably one wouldn't realize that this could be true if unless one really tried, you know, for some reason tried to prove it. It's just kind of unexpected and should know.
I have some like questions. So previously, the classical affine Grassmannian can be thought of as being reductive scheme.
Yeah.
In this case, can you say something like regardless of the Dean proper Darman?
Yes. There's a result like that. And I think in partially proper spatial diamond maybe. It's discussed in the Berkeley notes of Scholze, like all these representability property.
Yeah, I have a couple more questions. So one question is, so in this result, in this analytic result, is it correct that the role of bun G is not playing a role in the argument?
Right. Correct. So somehow the Fark-Fontaine curve and bun G on the Fark-Fontaine, like G-torsors on the Fark-Fontaine curve, don't really play an argument. Like if you try to pursue this kind of variant where maybe no sheafification is needed at all, then think in terms of analogies, then you could try to glue your torsor with respect to the trivial torsor on the complement of infinity on the Fark-Fontaine curve, get the torsor over all of that Fark-Fontaine curve, and then try to perhaps prove Gabor-Pullen matching in a sense. I mean, that's speculative, but if you could move something like that, and that would be in the direction of no sheafifications at all. But yeah, right. The argument here is kind of, it really is simpler than the classical setting, because the analytic topology of onadic spaces is somehow more pleasant than the Zariski topology, in that if you take all neighborhoods of your point and you take that kind of filter direct limit, then you're obliged to complete in the end to not fall out of the category that you want in. But once you complete, then you get just the residue field. And in the, for usual Zariski topology, take all the neighborhoods, you get the local ring, which is a lot more complicated than just Zariski.
One further question I had was, when you do this, is it you said you apply or use the Kęstutis conjecture for DBRs. A priori, is it possible that higher rank evaluation will appear when you take these kinds of limits?
Yes, but that kind of does not matter because the B theorem only does not depend on the plus ring, but only on the kind of the perfected field, and so it's still at the plus.
Would you expect some kind of triviality result? G-torsors over the open part quantity curve. Not sure that there's one. Is there some?
Yes, so I think if I'm not mistaken, in the paper of Kęstutis, where he studies G-torsors over a Fark-Fontaine curve, there is a result that if a torsor is trivial at a point, then it's trivial on the complement of that point, which is the analog of this. If a torsor is trivial at a point, then it's actually trivial on the complement of the point. That's kind of an analog of this in that sense. I think he actually proves this. So in fact, this classical theorem, there's also a paper of Kęstutis fairly recently in Contram de Determinations, where he reproves this classical theorem using Tanakian formalism. It's a really nice argument. At some point, it uses Habushi's theorem. That's how reductivity assumption is important. Habushi's theorem is about geometric invariant theorem about geometric subspaces. But anyway, so this classical kind of theorem can be reproven in a very pleasant way using Tanakian formalism. And that's also what he does in the Fark-Fontaine curve setting. So somehow the arguments are, one argument is part of the other. Anyway, yeah, the argument like works in both settings in some sense.
So that's Kęstutis' paper was about.
There's the Tanakian classification of torsors of the one or something like that. It's CRAS.
Sorry, and you said that also gives a reproof of this classical.
Yes, so sorry. So that paper is about this classical theorem. It's about reproving this classical theorem, some refinements. And then there's another paper about torsors on the Fark-Fontaine curve. Maybe it's mathematical element or something like. So there's another paper. I don't precisely remember the journal, but its title is something like classification of G-torsors on the Fark-Fontaine curve or G-torsors on the curve. A bunch of these results were done already by Fark, but if I understand correctly, maybe Fark was excluding the positive characteristic case and maybe cut some assumptions. And anyway, the Kęstutis approach that does it kind of more cleanly. Yeah, there's a paper which the techniques of this and the techniques of these two papers are somehow similar, but the settings are different. One is in this classical P1 setting, the other is different.
Thank you, students, again.